Alright, and now we're into the challenging part of this review. Dun dun dun. So I'm going to use red for this one. So, number 21. What is the approximate ionization energy of carbon? Well, I see this weird graph. I have atomic numbers going on. And then in the middle of it, I can see element symbols. And then I have ionization energy on my y-axis. So, if it's asking for ionization energy, my answer is going to come from this axis. It's asking about carbon. So I have to find carbon in here. Let's see. There's hydrogen, helium, lithium, beryllium, boron, carbon. Found it. It's right here. So carbon is approximately, let's see, maybe call that 1200. 1200, and you always have to write your units. So kilojoules per mole. Cool, that wasn't that bad. So let me find the approximate ionization energy of cesium. I know cesium has an element symbol of Cs, so I have to find Cs somewhere in here. So hydrogen, helium, lithium, beryllium, blah, blah, blah. No, 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 no. Sodium, magnesium, phosphorus, argon, potassium, zinc. No, 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 no. Ah, there it is. Cesium. So if I draw a line across, kind of crooked, it's okay. That's about, maybe like 300 kilojoules per mole. Per mole. Remember your units. And last one for this one. What is the approximate ionization energy of Krypton? Krypton is a noble gas. Sounds like the Superman's weakness. So Krypton is Kr. So I have to find Kr somewhere in here. Let's see, where is Kr? If you've spotted it already, good for you. You are awesome. Oh, found it. There's Kr. So I'm going to draw a straight line across to my y-axis, and that is about 1400 kilojoules per mole. And that is how you find those questions given a graph like this. Alright, so we're going to move on to the Lewis dot structure. So first things for Lewis dot structures or diagrams is you have to find the number of total valence electrons that you have to draw. So carbon is in group 4, so it has 4 valence electrons. Chlorine is in group 7, so it has 7 valence electrons. But I have 4 chlorines, so I have to multiply that number by 4. So 4 plus 7 times 4 is 28. That is 32. So I'm going to have 32 valence electrons here. So the first thing I'm going to do is draw a skeleton of what this might look like. Because I have 1 carbon and 4 of these ones, I'm going to draw carbon in the middle and draw chlorines around it. Then I'm going to attach them together like this. Each of these lines represent 2 valence electrons like that. You can draw them as dots or as lines. I'm going to draw them as lines. And then I have to go in and figure out where the rest of these valence electrons go. So I've drawn 2, 4, 6, 8 so far. So let me start with my outside. Because my middle carbon atom already has 8 valence electrons, it is happy. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. And that's it. I'm done. The shape of a molecule like this that has a central atom with 4 things attached to it is called a tetrahedral. So an atom with 4 things attached to it is called a tetrahedral. Alrighty, gonna move on to this next one. So I have HCN. So I have 3 different atoms instead of just 2, which is what you're used to. So H, I have to figure out the number of valence electrons. H is in group 1, so it has 1 valence electron. Carbon is in group 4, so it has 4 valence electrons. And nitrogen is in group 5, so it has 5 valence electrons. So now there's 1 of each, so I don't have to multiply anything, and now I can just add. 1 plus 4 is 5, 5 plus 5 is 10. I have a total of 10 valence electrons here. Okay, so this one, because there's like no way of putting like a central atom anywhere, I'm just going to kind of draw them next to each other like this. And now I need to attach them together. So I have 2, 4 valence electrons here. 1, 2, 3, 4. A line represents 2 valence electrons. And I need to put 6 more valence electrons. So I know that hydrogen isn't going to have any more because it already has its happy 2 valence electrons that it always needs. So I have to put them somewhere on carbon or nitrogen. I know that carbon is going to want 4 more valence electrons, and I know that nitrogen wants 6 more, so they have to share. So for carbon and nitrogen, what's actually going to happen is you're going to have 2 more pairs of shared electrons. So now, if you see, carbon has 2, 4, 6, 8 valence electrons. Carbon is happy, hydrogen is happy. Let's see nitrogen. 2, 4, 6, missing 2, 7, 8. So that is how you would draw this molecule. This has to do with some formal charges stuff. You're also probably thinking like, well, why couldn't it be just one line and then valence electrons around it? It's because this way, this molecule likes to be more stable. So this is how you would draw that molecule. And this shape is actually going to be a, I think it's a linear. Yeah, I'm pretty sure it's a linear shape. It's just a straight line. That's what it looks like. This one kind of looks like a weird, like little tetrahedral like this. All right, CO3 2-. What? I got an ion in here? Okay, so for CO3, I could have a central atom here because I only have 1 of this and 3 of these. So I'm gonna draw a C in the middle, and then I'm gonna kind of like spread out my oxygens. Okay, so I have, forgot to calculate how many valence electrons. So carbon is in group 4, so it has 4 valence electrons. Oxygen is in group 6, so it has 6 valence electrons. But I have 3 of them, so it's 6 times 3. And that is all. So I have 4 plus 18, 19, 21, 22. That's 22 valence electrons. And then you're like, I'm done. But no, you're not, because you have a 2- ion. That means you are 2 more negative than what you actually thought. So you need to add 2 electrons. So you actually have 24 valence electrons here. Okay, so let's start with my oxygens. Let's see what my oxygens can hold. Okay, so 2, 4, 6, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay, so now I have 24 valence electrons here. All of my atoms have a full set of 8 valence electrons. Yes or no? The answer is no, because my carbon only has 2, 4, 6. So carbon is really angry at me because he didn't get a full set of octet. So that means that one of these oxygens is going to have to share its own pair of electrons into carbon. So this one's going to be a double bond. So now I have 2, 4, 6, 8 around carbon. So 8, 9, 10, 11, 12, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And we're happy! Yay! Everyone has a full set of 8 valence electrons. So now, how I represent this 2- into a Lewis dot structure is I'm going to put the whole thing in brackets, and I'm going to say 2-, and that is it. This shape, when you have 3 things coming off of my central atom, is called a trigonal planar. All right. Next, beryllium and Cl2. So beryllium is in group 2, so it has 2 valence electrons. Beryllium has 2. And chlorine is in group 7, so it has 7 valence electrons. But I have 2 chlorines, so I have to multiply that by 2. So I have 2 plus 14. That is 16 valence electrons total that I have to put in here. So I'm going to start with my Be in the middle because there's one of that and 2 chlorines. So I'm going to connect them like this, surrounding my beryllium. So I have 1, 2, 3, 4 valence electrons so far. Let me try to fill in chlorine. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That's it. I'm done. And then you're like, well, wait, beryllium doesn't have 8 electrons around it. Remember, beryllium is an exception. Beryllium does not need anything other than 4 valence electrons. It is an exception because it only has 2 energy levels, so it doesn't need the full octet. Okay, so this shape is also a very straight line. It is called linear. Last but not least, we have our handy dandy water that we consume every single day. Hydrogen is in group 1, so it has 1 valence electron, but there are 2 hydrogens, so I have to multiply that by 2. And then oxygen is in group 6, so I have 6 valence electrons here, and there's only 1. So 1 times 2 is 2, 2 plus 6. I have 8 valence electrons that I need to put in my model here. So I'm going to put oxygen in the middle and connect my H's to it. And that's 1, 2, 3, 4. My H's are happy because they have 2 valence electrons that are touching it. So I have 4 here. I need to put 4 more. 5, 6, 7, 8. Boom! The reason why I did it like this is because these lone pair of electrons are actually going to like push my molecule down. It's going to bend my molecule. So water should be like this, like a straight line. Oh, let me do it like this. Water should be like this, like a straight line. But when I add a lone pair of electrons, it goes boop. And then when I add another one, it goes boop. So it bends it. And because of that, this shape is called a bent shape. These lone pairs of electrons actually bend my structure down. And it bends it. So it's bent. All right, and last but not least, you're gonna watch me do a graph. Woo, so fun, Ms. Rodriguez. I love it when you do graphs. Said no one ever. Okay, so Ms. Rodriguez collected 4 samples of gold. She weighed the mass and found the volume of each sample. So each of these samples are of gold. I found the mass and I found the volume of each one. I have to graph mass versus volume for the gold samples. Great, so I know that I have to title it. So I'm gonna say mass versus volume of gold samples. Cool, I got a point because I titled my graph. Then I have to label my axes. So this one, I'm gonna say that it's mass because it's in the left side of the table. Usually means that it is an x-axis variable. Because it is mass, I cannot forget the unit. Mass is in grams. Mass is in grams. That means that my y-axis is going to be volume. I cannot forget my units either. My units for volume are milliliters. Cool. Next thing I have to do is scale my graph. So with mass, I have my smallest number 2 and my largest number 6.5. So I have to fit a total of, let's see, whoa, hold on, my calculator is being all funny. It's like, oh, you're recording a video? Well, let me mess it up. There we go. Okay, so 6.5 minus 2 is 4.5. I have to fit a total of 4.5 points down here. And I have to use most of it so it can be very, very clear. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. I have 19 little lines and I have to fit 4.5 points within those 19 little lines. What happens if I fit, let's see, 1 point per every 3 lines? That would be 1, that would be 2, that would be 3, that would be 4. Nah, I would have too much space left over. Maybe 1 point every 4 lines. 1, 2, 3, 4. Yeah, it's good. So every 4 lines, I can have 1 point. That'd be my 2, that would be my 3, and that would be my 4. Cool. So I've scaled my X. I've used most of my x-axis. Now I have to scale my y. So on my y-axis, my smallest number is 3.3 and my largest number is 10.8. So 10.8 minus 3.3 is 7.5. I have to fit 7.5 points on my y-axis. Let's count how many lines I have to work with. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. I also have 19. So I know I can't do 4 per every point because there's no way I would reach it because I tried it already here. So maybe let's do every 3 points. What happens? 1, 2, 3. Ooh, look at that. I caught a mistake here. So even though I can fit 4 points in here, I should actually start at 2 and go to 6 instead of 1 to 4 because this would not allow me to fit all of my data. So let me go back and fix that mistake. This is actually 2. This is actually 3. This is actually 4. This is actually 5. Oh, I actually messed up here. Hold on. 2, 3. Oh, it's because of 0.5. Yeah. All right. That's fine. We can call that 6. Okay. So let's try to do this one right. So I have to start at 3. Let's say that every 3 lines is a point. So 3, 6, 9, 12, 15, 18. That's a kind of small because then I wouldn't be using like this much of it. Let's see if this one is every 3. So 3, 3, 6, 1, 2, 3, 4, 9, 12. Yeah, let's do that one. So every 4 lines, I'm going to be going up by 3 points. So this one's going to be 3, 6, 9, 12. Still not using most of my graph, but I'm using a good chunk of it. Okay, so scaling is probably like the hardest part about doing a graph, just because you have to like divide your points within these lines, and then that just gets messy. Okay, so for my mass that has 2 grams, my volume is 3.23. So 2 grams, my volume is 3.3. So let's say that that's like about right here. And that's sample number 1. For my mass that has 3.5 grams, so 3.5 grams, my volume is 5.8. So 5.8, and let's call it about here. That's my sample 2. For my mass that has 5 grams, my volume is 8.3, so that's about, yeah, like right here somewhere, 3. And for my mass that has, sorry, my dog is whining in the back. For my mass that has 6.5 grams, my volume is 10.8, so like right here. Do not do what Ms. Rodriguez just did here. This is just for the purpose of continuing on. Do not do this. This is wrong. I would not get any points for this point right here. You have to fit everything within here. Okay, so then I'm going to draw a line across through it. Boom. All right, so if you know how to find slope, slope is equal to y2 minus y1 over x2 minus x1, you'd be able to find the density of this. So you can always find it with the slope. How I prefer to find the density is actually just take each one and see if they are close in answer or not at all. So number 26 is calculate the density of the gold Ms. Rodriguez found. Round to the 100th place. Okay, so I have to have 2 decimal places. So I can take whichever one I want, really, just to make sure. I'm going to go through each one. So I know that density is equal to mass divided by volume. So for sample 1, I have density is equal to 2 divided by 3.3, and that is 0.61. 0.61. Well, I'll write it right here. And then for my sample 2, I have 3.5 divided by 5.8. That is 0.60. And then I have, for sample 3, 5 divided by 8.3. That is equal to 0.60. And then I have 6.5 divided by 10.8. And then I have 0.60. So most of these answers give me a density of about 0.60. So I am going to say that my density is about 0.60. And then you have to put the units, grams per milliliter. Make sure that you show your work. If you found it this way, you have to actually write out the formula and write out your points. If you found it this way, you have to write out the formula and write out your points. Last one. Based on the density you just found, so this one, my density is equal to 0.60 grams per milliliter. What would be the mass, so mass is a question mark, of a 20 milliliter sample, let's supposed to say sample of gold. So volume is 20 milliliters. So I can use my density formula again, yay! So I can draw my handy dandy triangle. I was about to call this a square. That's wrong. Density is equal to mass over volume. And I can use this to solve for M. So M is going to equal density times volume. They're right next to each other, so density times volume. Density times volume. So M is equal to, density is 0.60 times my volume is 20. Let's look at what that is. If you know what that is already, then you are a genius and you should be teaching me. Times 20. That is 12. So my mass is equal to 12. But I'm not done yet. I have to put my units. And mass is always in grams. So that's my answer. 12 grams. And then we finished. Yay! So rewatch this video if you need to. Study. Watch my videos. Study with me. Bye.